Okay, so I guess we can start again. Everyone is here. Just a very brief recap of what we learned so far about dark matter production. Yeah, so we've considered these kind of processes, dark matter particles interacting with heat bath particles, typically standard model particles. And then basically freeze out is determined by strong enough interactions to keep these particles in equilibrium by this interaction. Yeah? So that means we follow the equilibrium distribution and then freeze out at some point. And the larger the interaction rate, the longer we are in equilibrium, and therefore the final abundance will go down. Yeah? Freeze in is determined by the condition that these interactions are very feeble, so it is only this direction of the production that is relevant. So we constantly produce from the heat bath, but never reach equilibrium. Yeah? So then we have a production curve that looks like that. And then at some point we freeze in, so we asymptotically stop producing, simply because the energy in the heat bath is not sufficient to produce very massive particles. Yeah? So that's this FIMP case, meaning that the stronger the interaction, the larger the final abundance will be. The more we produce because we constantly produce. And then I, hopefully convinced you yesterday that even though physically this is the direction for the production, you can mathematically formally write it as a process in this direction. So that means that this one here is actually the annihilation cross-section. Yeah, and the only thing that you need to remember in this expression then, so this is the actual dark matter density for which you want to solve, but this is the number density of a would-be distribution of non-relativistic particles in equilibrium. Yeah, so then this is mathematically the exact description of this, even taking into account like complicated temperature dependence, like quantum statistics and so on. Yeah? Okay, any questions about this general setup? Okay, great. So then let's briefly discuss this kind of equation. Yeah, I already stressed like why this is like a much more efficient way of formulating things than in the physical direction. I also said that from a practical point of view, it's nice because now you can directly integrate this. Yeah? So on the left-hand side, you just have a time derivative, and on the right-hand side, you don't have a dependence on the dark matter density. So this is just a function that is a function of temperature or time. So we can just integrate it. Yeah? So let's first ask, when do we dominantly produce FIMPs? Yeah, and that depends on what kind of interaction we have here. Yeah, so naively, you can of course say, okay, let's just do some vanilla interaction, as we also did in the FIMP case. So let's assume that this is a renormalizable interaction. So some kind of, the matrix element would be dimensionless, of course, and the cross-section could be parameterized like some coupling squared divided by a mass squared. Yeah, but, if you think of these small numbers that we will need, we need very small couplings, then of course it's natural to think that, well, maybe we can achieve this, or it's a particularly natural way of achieving small interaction strengths by some effective field theory approach. Yeah, so that means that we have a non-renormalizable operator, some dimension higher than 4 operator, that is then this suppressed by some mass scale. Yeah, so let's say that this scales like that. Lambda to the minus n, lambda is a dimensionful parameter. So that would be the cutoff scale where your effective theory would cease to be valid. Okay, so then we can estimate what happens. So then our sigma v n squared, so that's this one. So let's look at the high energy limit. So we look at the limit of very large temperatures. Then how does this one scale? Well, this is the matrix element that scales like this. So we will, of course, from the matrix element, we square to get the cross-section. So this is something that we can't avoid. Yeah, but then by dimensional analysis, the only energy scale that we have at high energies is the temperature. And of course, the cross-section should still go like 1 over mass squared. Yeah, so that means for a dimensionful coupling, we must make sure that this is a 2n minus 2 scaling for the cross-section. Yeah, and then, well, we have an n squared. So n in equilibrium goes like t cubed. So this is a t to the 6. Yeah, so on the other hand, we can compare the relevant scale here. So h times n. Yeah, that at high energies will scale like t to the 5. Yeah, so t squared for the Hubble times t cubed for this one. Yeah, so and then you see that, well, basically from this you can deduce which is more important, like where will the dominant production happen, by comparing the two. So dominant production for, well, okay, what happens? Let's say that n is 0, or maybe even smaller than 0, so in any case, something that is renormalizable. Yeah, then the scaling is such that this is a t to the 4, and this is a t cubed, a t to the 5. Yeah, so that means the expansion, the dilution, dominates at large temperatures. In other words, the production will dominate at low temperatures, at the lowest temperatures possible. So this is IR dominated. Yeah, so that is basically the case that I sketched here. When the production stops, and well, this is a log-log plot, so it's actually the dominant production in this regime, roughly the scale of the dark matter mass. Yeah, so this is for T around the dark matter mass. So this is called IR freeze-in. Yeah, but on the other hand, if n is larger than 0, n is an integer, then it's exactly the other way around. So then the production term dominates over the expansion term at high temperatures, at early times. So the dominant production will happen, I mean, it will not actually follow this curve that I sketched, but it will happen at very early times, and then the production will become less and less important. So in other words, we will be sensitive to the highest temperatures available, so that will be the reheating temperature. Yeah, so that's a UV dominated freeze-in. Sorry, that's a freeze-in. Yeah, so these are very different situations. It just means that if you actually consider these kind of non-renormalizable interactions, you have to basically, I mean, this kind of framework doesn't make a lot of sense in general anymore, because then you should really think about a model that also describes the reheating part. So you should include an inflaton in your description. You should include direct couplings of the inflaton to dark matter particles and so on, at least if you want to do really precision calculations. Okay, so then let's check what happens for the infrared dominated freeze-in. What kind of couplings do we need? Yeah, we had a simple estimate for the case of freeze-out production, for wind production, and for freeze-in production, we can do something similar. Yeah, so let's say that we parameterize this by some effective coupling alpha and dark matter mass. Yeah, so then we basically should, analyze this equation. So first of all, this here, as I mentioned before, is basically just the time derivative of the co-moving number density. Yeah, so what we have here is an a cubed n chi, and then you should have an a to the minus 3 here, and then you get exactly that, so that's, I pull to the other side. So we have an a cubed, and then we have an n Maxwell-Boltzmann squared, and our sigma v. Yeah, okay, so then we can basically just directly integrate this. Yeah, so that means that at freeze out or freeze in, we will have the number density, Maxwell-Boltzmann, sigma v, and just the time of freeze-in. So we want to evaluate all of this at the freeze-in time. So freeze-in happens at around the mass of the dark matter particle. And you remember that, well, there's one time scale that we have, that's the Hubble rate. And during radiation elimination, the Hubble rate is indeed just 1 over T with an order unity factor. So that means that my time freeze-in is just the inverse Hubble rate at freeze-in. So in other words, this is Max Planck, the Planck mass divided by the freeze-in temperature squared, and that is roughly the Planck mass divided by the dark matter mass squared. Yeah, sure, but like the point is that you have the dominant production in this regime, and then the dominant contribution from the integral will pick up this spot here. Yeah. So basically, you start with a tiny initial production and then continuously build up the production. This is basically the estimate that we just had here. So if you sort of look at this logarithmically, the largest contribution comes from T roughly chi. Okay, so then, you see that we have an A cubed here, so we actually can express everything in terms of the physical number density. This one is roughly T to the 6 at freeze-in, so that's a m chi to the 6. And then we should also estimate the n chi, and for that, the one that we need in order to get the correct relic density. And that's the same estimate that we did before. So n chi at freeze-in. So at freeze-in. What's that? Well, it's the matter density of the dark matter particle divided by the mass. And then we express this in terms of the matter density, the dark matter density at equality. So that's just redshifting after it decouples. So we have a T freeze-in, which again we take to be the dark matter mass. So m chi divided by T eq cubed. And then the reason why relate this to the dark matter density at equality is, of course, well, equality means that all the densities are about the same. So this one here is the same as the photon density, which is just Tq to the 4. So that means that this number density that we want in order to get the correct relic density is roughly Teq times m chi squared. Okay, so then, well, for the sigma v, we made the ansatz that this is an alpha squared by m chi squared. Now let's see. For the t, we have m chi to the minus 2. Here's another m chi to the minus 2. There's an m chi 6, so an m chi squared that is left. We have also an m chi squared on this side here. So the dark matter mass dependence drops completely out. In other words, what we have is alpha squared, just the ratio of the Planck mass divided by Teq, not the other way around. So you bring it to the other side. So in other words, this is Teq over m Planck, and that's roughly 10 to the minus 10. So that's grossly different from the case of freeze-out. So in the case of freeze-out, the requirement to get the correct relic density fixed the cross-section to be of a fixed value. So that was for example, the electroweak cross-section. And then we said that, okay, it actually fixes the ratio of alpha by m. While for freeze-in, the mass dependence drops out. So what we fix is not sigma v, but sigma v times m squared. In other words, we fix alpha. So for freeze-in, in other words, there's only one value, give or take order unity factors, that gives you the correct relic density. It's not just the ratio. Great, yeah. And then in principle, I mean, this is just an application of why dimensional analysis is so nice. So if you think about this, yeah, you have like one-dimensional quantity that you measure today. That's the dark matter density. But you have three-dimensional quantities that you can play with. Yeah, you have the dark matter mass, so some scale at which the annihilation happen. You have the Planck mass, which tells you something about the Friedmann equations. It's basically the expansion rate of the universe. Yeah, and you have another scale. Well, I mean, the scale that is actually, when I said that you have the dark matter density today, the measured one, that's the time of equality. Yeah, so saying that we want to have the measured dark matter density is basically just saying that at equality, it's about the same as the photon bath. Yeah, and then it's just a question of how you can combine these three dimensionful quantities to get a dimensionless coupling. And then freeze in and freeze out basically realized two different options. And well, maybe today, in any case tomorrow, we will see yet another option. Okay, good. So then what about detection prospects? For FIMS? Well, I mean, this one here, yeah, we just derived. So that's what we mean by feebly interacting. Yeah, so basically no. Yeah, there's no hope to see these kind of couplings in any kind of direct dark matter searches. Yeah, so there are like a few exceptions. Yeah, so one is if you have a very, very low reheating temperature. Yeah, so by very low, I mean something that is hardly much larger than the temperature for a BBN. Yeah, so formally, I mean, it's sort of hard to motivate this from a model building perspective, but formally, it's not excluded. Yeah, and then you can play games with these kind of considerations here, because, of course, if you have something that is IR dominated, UV dominated, and the reheating temperature is very low, yeah, compared to the dark matter mass, then you don't have a lot of time to produce dark matter, meaning that the coupling that you need will be much, much larger than the generic estimate. Yeah, and this sounds like, okay, you have to do a lot of model building, but it turns out that even in this very simple model of just a scalar singlet that I mentioned in the context of freeze out, this can be already relevant. Yeah? So if you look just as, again, a model that is described by this one, where the scalar singlet, so just a real scalar degree of freedom, neutral under the standard model gauge group, is produced now with via freeze end production. Yeah? So you have just like a very small coupling here in principle, but then if reheating is very low, it means that this one here, I mean, this is of course a renormalizable coupling, yeah, but effectively, I mean, you get this kind of diagram then. Yeah, you have annihilation via the standard model Higgs boson. And if you only consider temperatures, energy scales that are much smaller than the Higgs mass, a few GeV maybe only, or even sub-GeV, then this becomes an effective dimension 5 operator. Yeah, so we are back to a situation where we're actually dominated by the UV, which in this case is not very UV at all, just slightly larger than BBN scales. Yeah, and then you need actually couplings that are sufficiently large to be tested either already now by the invisible decay width of the standard model Higgs or by projected sensitivities. Yeah, so that's one option. And the other point how you can test this is if you have freeze-in production of very light dark matter. Yeah, because, I mean, you still produce from the thermal bath. Yeah, so you inherit a velocity distribution from the plasma. Yeah, so you get a non-negligible free streaming length. Yeah, so then you get constraints from structure formation and yeah, the free streaming length. Yeah, so I mean, and that gives a limit. So I mean, typically this constraint on the free streaming length on light dark matter is expressed in terms of something that is called a warm dark matter candidate, which is not quite, I mean, it's a very specific object, which is not quite the warm dark matter that we have discussed in the case of a simple freeze-out, but it's just a way of quoting this limit. Yeah, so let's say that this is a limit. Of course, there's discussion in the literature of what is the limit, but I mean, for this, I mean, one possible limit, I mean, not the most stringent one, but also not the most conservative one, is quoted to be about 3 keV. Yeah, so there's an order of 2 maybe uncertainty in that. Yeah, and that corresponds to a limit on this on FIMS of about 9 keV. Yeah, so, and then they scale correspondingly. So if you find a different limit in the literature on warm dark matter, you can correspondingly, roughly at least, scale the limit on your FIM-produced model. Yeah, so these are the basic ways of how you can actually probe FIMs. Of course, well, also those prospects are much more feeble than in the WIMP case. Okay, so these two ways of producing dark matter from the thermal bath, I would say are clearly the two that are most often discussed. But then in recent years, there has been quite some interest in exploring alternative routes. And I would just want to give you some ideas of what can happen. So roughly, I mean, if you think about the diagram that I just wiped out, there are 2 options. You can change, you can play with the number and type of external particles. So for example, you can consider something like that, where you have a, well, in the case discussed so far, we had an interaction of this type. And you can, of course, turn it around, and we discussed kinetic decoupling and the like. But then one thing you could discuss is changing the number of dark matter or standard model particles that are involved here. So for example, you could have such a diagram or such a fundamental interaction. And this is an option that is, I mean, again, you can discuss both ways, so what corresponds to freeze out and what corresponds to freeze in. So if you consider these kind of interactions to be strong enough to keep the dark matter particles in equilibrium at early times, this is referred to as semi-annihilations. And on the other hand, if dark matter production only proceeds in this way, you start from a very small initial seed and then produce more dark matter by interacting with the heat bath. This is referred to as dark matter from, well, you can call it exponential growth, and I will say a bit more about this. And you will also understand why, pandemic dark matter. So another option is to neglect or get rid of the heat bath particles altogether. So we basically have something like this. Okay, so this wouldn't help at all, because this is, I mean, a diagram that doesn't change the number density, the number of dark matter particles, so you can't produce dark matter in this way. But what if you add another dark matter particle here? Then it's actually a number changing process, and if it is strong enough, this interaction, just the dark matter interactions with each other can thermalize the dark matter bath, the dark matter population. So this is referred to as SIMP, or strongly interacting massive particles dark matter. And I want to discuss, this one and this one in some more detail. So let's start with a pandemic case. So we consider only production. So that means that we want to start with a situation where the dark matter density is strongly suppressed, like in freezing. And will also stay strongly suppressed, just like in freezing. So that means that, you can immediately write down the Boltzmann equation. For ordinary freezing, we had a sigma v n chi squared in equilibrium. But now, we basically replaced one of the dark matter of the heat bath particles with a dark matter particle. So then instead of heat bath number density squared, we get a heat bath number density times dark matter density. So if you find it confusing that I started with an n psi squared here, the way we wrote it was an n dark matter squared, but I stressed that this was not actually a dark matter n. It's a would-be dark matter n, and physically it was actually an n psi squared that we had there. Okay. Good. Okay, so what is this? So again, this here is just a time derivative. So what we have here is time derivative of n equal to something proportional to n. That's exponential growth. And of course, you don't have to know fundamental differential equations to see that. You see that also directly from the picture here. Because if you start with one dark matter particle, by this interaction you get 2. From 2 you will get 4, you will get 8, and so on. So that's exactly the exponential growth described by this equation. So in other words, in our standard sketch here of co-moving number density, as a function of time, we start with some tiny initial abundance, wherever that might come from. Could be directly produced from the inflaton, could be radiated from primordial black holes, wherever, whatever. Phase transitions, we don't have to specify this. Then at some point, you will, the production here will become relevant. So you have an exponential growth phase. And then, again, at some point, the Hubble expansion takes over because the production part here is suppressed. So why is it suppressed? Again, for the same reason as in the freeze-in case, you basically have to have sufficient energy in the heat bath particle to produce the rest mass here. So this will happen at around 1. So there's a natural end to this exponential production. Okay, so why do I also call this pandemic dark matter? It's a simple reason. If you look at this equation, exactly the same equation you can use to describe the spread of diseases in a population. So the same equation can be used to, or is in fact, in practice, used to describe the spread of diseases in a population. So this is known as the SIR model. SIR compartmental model, and the way it is typically written is in this way. So I should introduce all these things. So I is the number of infected individuals. S is the number of susceptible individuals, so those that still can be infected. Susceptible. And R, so the total number minus S minus I, is the number of recovered individuals. So, let's say it's tot. So this is the total number. And then, well, if you compare the two, there's a one-to-one correspondence. So beta, well, okay, so let's first continue here. So beta is then the infection rate. And gamma is the recovery rate. So when you compare to this equation, you see that, the infection rate is basically given by our sigma v, and the recovery rate is the Hubble rate, the Hubble expansion. This works surprisingly well. You can also check out the first archive version of our article to see how well this works. You can wonder about recovery. So in the case of dark matter production, of course, there is in some sense no recovery. So we produce dark matter particles all the time, and the resolution here is that we have a recovery rate because this is the physical number density. So the physical number density is of course redshifted, and that in terms of this model means that it goes down, so there's a recovery. But if we instead write everything in terms of the co-moving number density, the co-moving number density always increases, then the h goes away. We just have a time derivative of the co-moving number density. So in our model, unfortunately, there's no recovery. Good. Okay, so then how does this compare to other models? Not models in medicine, but models in physics. So by this I really mean more like mechanisms. Maybe I should even write mechanisms rather than concrete models. So how does this compare to the freeze-in and freeze-out production that we've discussed so far? Then we can consider a simple toy model where we say that, okay, let's say that everything is just scalars, and we have point-like interactions between dark matter particles and heat bath particles of the freeze-in type. So this is just some coupling, which we call, let's say, lambda fi for freeze-in. This is the kind of coupling that we needed for freeze-in, of course also for freeze-out. And then we have another coupling type like this, and that's what we can call lambda transmission. Transmission motivated by this analogy here. Okay, and then we can explore where in parameter space we can recover the various production mechanisms of such a simple setup. So how many parameters do we have? We have two couplings, two independent numbers, and then we have two masses. So it's a bit tough to draw a four-dimensional diagram on the blackboard, so I need to fix something. One thing to fix is obviously the dark matter density. We want to produce the correct relic density, but I need to fix something else. And one nice way of representing everything is to fix the mass ratio. The result will not be very dependent on this, but I have to fix something to have a 2D plot. So I want to fix the dark matter density. to the correct value. And let's say for the purpose of what I will sketch, I choose a situation where the standard model particles are actually slightly heavier than the dark matter particles. This simple model, by the way, makes sure that also dark matter cannot decay, so it's actually stable, just on for kinematic reasons. Okay, so then we get a complex plot. So the remaining two parameters are just the two couplings. Okay, and then I can add some rough numbers. So this is 10 to the minus 10. This is the scale that we would expect for freeze-in from the estimate that we just did before. And then let me put another sort of benchmark that's around 10 to the minus 5. And here we have a 10 to the minus 8, and here another 10 to the minus 5. Okay. Then in this, you can call this basically a phase diagram of dark matter production. So in this phase diagram, we learned already that freeze-in, that is something that must happen at around this coupling scale. So we will have some parameter space like this. Well, colors don't work out very well. And of course, this is in the situation where this Newt coupling time is small. So that's why we will have it in this part of the parameter space. Then we have also discussed freeze out. So that's this type of coupling. So we know that we will always get a solution for the correct radic density if the lambda is larger, significantly larger than for the freeze-in couplings. So we know that, we can first start at the bottom of this plot, so neglecting these transmission couplings. So then we know that we should always fix the ratio of the coupling strength and the mass, meaning that here we will get a much larger ratio. So for small masses, so we will have something like this. And then if we increase the mass, we will get here. So by small mass, I took the smallest mass that I can have, namely around an MeV, before the existence of these heat bath particles would be in conflict with BBN observations. So they would add too many relativistic degrees of freedom, so contribute too much to the Hubble rate. So this region in between here is basically excluded by BBN then. Okay, and then I can get this all the way up to the electroweak scale. Then the electroweak scale would correspond to a mass of around a TeV. Okay, so what happens then if we increase this transmission coupling further? So then we can, let's start here. So at some point when it's very strong, this freeze-out process will be dominated by, not by this diagram anymore, but by this diagram. It's still freeze-out, so this is from semi-annihilation. So then we have, so these lines are lines of constant dark matter mass. So then it looks something like that. So then the freeze-in or freeze-out coupling is not important anymore, and it's only driven by this coupling. So this is the regime of semi-annihilations. These are WIMPs, or freeze-out, let's call it. And this is freeze-in. So these are the only options, basically, if you wouldn't consider this pandemic production, to produce dark matter with the correct relic density. But then once you add pandemic dark matter, it occupies something like this part of the parameter space. So it's quite a significant part of this phase diagram where you can get the correct relic density from pandemic production. Again, like the empty regions here would correspond to so small masses, so MEV or sub-MEV dark matter and heat bath particles, so that's excluded by cosmology. Okay, I think that's a good point to take a break. So let's take a 10 minutes break and then continue. Okay, I guess we can start again. Are there any questions so far about this scenario? Or these scenarios? Yeah, so if not, let me finish this discussion by discussing a bit of model building. So basically, the question is then, how do we get into this parameter space in a bit more generic way? Because you can say that, okay, maybe we occupy some significant part of this parameter space, but maybe it's not a relevant part of parameter space. So how do we model something where this kind of interaction is much larger than this interaction, this type of interaction, in a generic way? So the question, in other words, how do we get a generic realization of, this is relevant for the Boltzmann equation, so cross sections where the transmission part is much larger than the Friesen part. And it turns out that there's really, of course you can just put it by hand, like in this toy model, then it's just a number, a model parameter input. But there is indeed a generic way of doing this, and that is by mass mixing and some mediator. So let me explain what happens. So mass mixing. So we have a Lagrangian that looks like this, where you have basically a dark matter particle that is charged under some gauge group. So let's say like a U1 gauge group, some U1 prime here. So it does not couple to the standard model. And the only way it couples to the standard model, or the heat bath, is via some small mass mixing between the dark matter particles and the standard model particles. So this kind of setup. So that just, in that case, you just need to make sure that the dark matter particle has the same quantum numbers as the heat bath particles. And of course, that's, if even this is a heat bath particle in the dark sector, this shouldn't be complicated at all. But then if you think about this, there's even in the standard model potentially a nice candidate, or and that's the neutrino. So this kind of setup should immediately bring you to the idea of looking at stereoneutrinos. So then the dark matter particles would be stereoneutrinos. You have a mass mixing, that's the standard way of producing stereoneutrinos in the early universe. And then the proposition would just be to charge these stereoneutrinos under some gauge interaction, or under some other interaction, because the whole thing works either with a vector boson here, or also with a scalar particle. So why does that work? Well, basically, if you have a mass mixing like that, what you should do is to, then you have a mass matrix that is not diagonal, so you want to diagonalize such that you have mass eigenstates. And that introduces then a mixing angle that is roughly like this. Yeah, so it's basically given by this dimensionful mixing parameter divided by the dark matter mass. Okay, and then, like, what kind of diagrams would we have? Well, we would have to consider these kind of diagrams. So we have dark matter annihilation into heat bath particles, and we have this diagram where we have both a heat bath particle and a dark matter particle. And we also have diagrams of this type where we have, well, of course, for the freeze-in part we only have this, yeah, but for this one here we have a something like this, chi, and chi psi. Okay, so then for freeze-in, yeah, so let me use the same colors. This is freeze-in, so this is an unsuppressed coupling, yeah, but this one here is suppressed by a mixing angle squared, yeah, because the heat bath particles are not originally charged under the U1 here, or coupled to the mediator. And then what else? For freeze-in, we have yeah, so this would be for freeze-in, okay, good. And then for the transmission process, on the other hand, we only have a, and that is relevant then here, my color. Yeah, so this coupling, on the other hand, is just a one order of the mixing angle. And here, the same, yeah, so this is unsuppressed. The dark matter particles are directly charged, and here we have one order of the mixing angle. Yes? Dark matter annihilation. Yes, in principle you should consider that as well, but that's a kinematic question, right? So like it depends on whether the dark photons are heavier than the dark matter particles or not. And also we want to consider freeze-in-like production. So we start with a situation where the dark matter density is very small. So we only go from this direction, and then it's basically a question whether the dark photons are already there, are part of the thermal bath, which in turn is a question of how large these interactions are. Okay, so that means that generically, yeah, the transmission type of couplings in such a setup will always be larger than the freeze-in type of couplings. Yeah, I mean, these are at the diagram level, you square to get the amplitude, to get the cross-section. So there's a difference between the mixing angle squared, or essentially sine squared. Yeah, and of course, you know from stereo neutrinos that we anyway have to look at small mixing angles. So for small mixing angles, it's exactly like this kind of setup will naturally bring you into this part of parameter space. And indeed, there's a concrete application then. And that's what you can call minimal sterile dark matter, sterile neutrino dark matter. Yeah, so just to recall, so in the standard model, if we only add the sterile neutrino to the standard model, yeah, that's what I call standard model neutrino production. Yeah, this is essentially a freeze-in production. I didn't have time to go through this in detail. So you basically, it's a combination of oscillations and scattering, electroweak scattering processes, like charged and neutral current interactions. Yeah, so you constantly produce them from the thermal bath, active neutrinos, then via mass mixing and oscillations will produce sterile neutrinos. Freeze-in production. Via oscillations plus electroweak scattering processes. Yeah. Okay, so just to be, maybe I wasn't clear. So electroweak scattering, yeah, so you have anyway active neutrinos. Yeah, so you would naively say that, okay, then these active neutrinos can oscillate to stereo-neutrinos, yeah, but they, of course, just oscillate back and forth, so that's not really a production. So you need additional scattering processes on the active part, which basically constitutes a measurement. Yeah, so then you project onto the physical state, which is then either, because of the oscillations, either an active standard model neutrino or a stereo neutrino. Yeah, so this is known as the Donaldson-Whitrow mechanism. It has been studied in a lot of detail and basically fixes the combination of stereo neutrino mass as a function of mixing angle to get the correct dark matter relic density. So in principle, such a stereo neutrino is an extremely nice dark matter candidate. Yeah, you would anyway expect it, sort of as an addition. I mean, it's a bit of a definition whether you call a right-handed neutrino part of the standard model or not. But since we know that we have neutrino masses, you certainly expect something. Yeah, so this is a very good, an excellent candidate really for dark matter. There's just one problem. Yeah, this is ruled out by observations. Yeah, so what's the problem? We have X-ray constraints. Yeah, so basically, if you have a stereo neutrino, yeah, it can mass mix into an active neutrino, and then you have like at one loop, you can radiate a W. Yeah, so in a charged interaction process, you have a lepton, and you get an active neutrino again, and radiate a photon here. Yeah, so that means the stereo neutrino is not stable. And since, I mean, if this is dark matter, today is its rest. So this is just the decay of a massive particle. The stereo neutrino mass would be order keV to get the relic density. And then for kinematic reasons, like it's basically a decay in the center of mass frame. So the energy of this one and this one are the same. Yeah, so what we're looking for is a monochromatic photon. And since it's keV, it's an X-rays. Yeah, so you're expecting X-ray lines from the center of high dark matter densities, for example, the galactic center. And, well, there are lots of lines, but they are all accounted for. We don't see this. And that's exactly what excludes this kind of production mechanism and this explanation as a dark matter candidate. Okay. So how can we alleviate that? And that's the reason why I call this minimal stereo neutrino dark matter. We just need to add one scalar degree of freedom. So we just add here a scalar mediator. And that basically opens up a new production channel. That means that we are not only restricted to this range here, but can explore all of this range and parameter space. So in particular, we'll allow this pandemic production. And that gives new viable parameter space. In particular, starting from the Donaldson-Whitrow production, you need a specific value of the, I mean, for a given mass, stereo neutrino mass, you need a specific value of the mixing angle. And, well, if you think about this here, freeze-in production means that by pandemic production, you can achieve the correct relic density with a somewhat smaller coupling. So we can do the same thing with a somewhat smaller mixing angle, but then this diagram would also be correspondingly suppressed because that's the same mixing angle. This diagram doesn't change in this kind of setup. So the X-ray signal will be suppressed. So we will be able to circumvent these bounds. But we also get further observational opportunities. Yeah, so, okay, first of all, this one here is not modified. Just, I mean, we would expect to see a signal, or at least in part of the parameter space, a signal just below current exclusions in their projected experiments, so they might see something. And then, of course, we have constraints on structure formation, so both the free streaming length and the impact on sound horizon from kinetic decoupling are relevant. So that is basically how, even in such a model, you can exclude like 2 light dark matter masses. So below a few keV, also this kind of candidate remains excluded. But then there's yet another one, and that is since we add a scalar, so a mediator here, that induces dark matter self-interactions. And therefore, the parameter space is actually bounded from below. So if we get to too small mixing angles, then of course we can evade these kind of things. But on the other hand, we have to basically, I mean, still make sure that we produce sufficient dark matter. And that can only be done by making the mediator here more efficient. So we need a larger coupling there, and that induces a larger self-interaction. So we have stereo-neutrino dark matter self-interactions. Okay, so that's just a concrete model building application. Okay, so the next thing I wanted to talk about is this SIMP dark matter, strongly interacting dark matter. So just to remind you, we have a diagram like that. So that means we have not 2-to-2 processes, but 3-to-2 processes. And, well, of course, one can generalize this to n-to-2 processes. I will get back to that. But the main point here is that only the dark matter interactions themselves can thermalize the dark sector. So dark matter can self-equilibrize. So let's try to understand what happens by looking at the rates in equilibrium. So if we look in this direction, then it should be a rate that is proportional to the number density squared, and it's in fact just an ordinary cross-section. So then we have something like n equilibrium squared sigma v. On the other hand, in this direction, it should be proportional to the number density cubed, because we have 3 initial particles times something, and, well, we just have to give it a name. So let's call it, and that's the standard way this is referred to, sigma v squared. But of course, in the end, I mean, I know that at least I was grossly confused about this v squared initially. So in the end, you should realize that this is really just a definition of what the rate is proportional to. So the rate is defined in the end by the collision operator. So you write down the entire collision operator, and whatever, I mean, the proportionality factor to n cubed, that's what you call this object here. Okay, so then we can again use detailed balance. So that means that in equilibrium, these 2 rates must be the same. And then from that you learn that, well, the dimension of this object here, what is that? It must be the same dimension as the cross-section times a number density. So in other words, this is mass dimension to the -5. So that means we can sort of parameterize this kind of object with some alpha, some coupling. Now I choose the parameterization alpha cubed because we have 3 particles participating divided by the dark matter mass to the 5. So this is what we will use for similar estimates as for the case of FIMP or WIMP production. Okay, so then what happens outside equilibrium? Then, well, I mean, like this direction is clear. So okay, so confused. So this would be just an n squared sigma v. Yeah, and this one, well, we want to make sure that, okay, sorry. Okay, so I can still use my detailed balance argument. Yeah, so these two things must be the same. Yeah, and I still want to keep the scaling here. So that means that I can write this as n squared neq sigma v squared. Yeah, so again, just managed to confuse myself. So I know that this must be of this form, this direction, yeah, but then I want to make sure that I recover detailed balance in the equilibrium case. And on the other hand, I want to make sure that I keep the scaling with n squared because that's what's physically happening. Yeah, so that tells me that the Boltzmann equation for this kind of process is again the Liouville operator, and the collision term will be given in this form. So I can again just write it in terms of one cross-section. So in this case, we have the 3 to 2 cross-section, and then we have an n3 cubed, n cubed, yeah, minus n squared times n equilibrium. So that's the Boltzmann equation to describe these kind of processes. Yeah. No, exactly. It's not the same temperature as the universe. We will get back to that. Yeah, so it's just equilibration, and so far we say that it's a completely decoupled dark sector, maybe, but we will get back to this equilibration point question. Yeah. So here in the NEQ, yeah, I have the equilibrium at the temperature where these particles equilibrize by only this interaction. Absolutely. This is the temperature, I mean, this is the actual temperature of the entire universe. Yeah. So we can again discuss when happens freeze out. Yeah, and now I will pretend that you did not ask this question. So for the moment, I will just assume that the temperatures are the same. Yeah, but keep this in mind. It's a very good point, of course. It's not obvious that we can assume this. Yeah, so let's say that, and I will get back to this, there are additional diagrams here that actually enforce the temperature of the dark matter particles to be the same as the standard model temperature. But it's not obvious. I mean, only from this diagram you don't get this. Okay, so freeze out happens again at, well, when this term is comparable to the rate here. So that means that freeze out should be sigma v squared n cubed. And then with our ansatz here, this is a alpha cubed m to the 5 n squared. And well, then we do the same estimates as before. So that means that our h, that is a t freeze out squared by m Planck. We have an n, that is a t freeze out squared. And on the other hand, we want to make sure that this gives the correct relic density. Sorry, this is the cubes here. So let's first solve for the. No, we want to solve for the correct relic density. So let's solve for the n here. Okay. So our n is by this estimate that we always did rho chi by m chi at equality. So times t freeze out by t equality cubed, and then this one is it's at equality, so it's the same as the radiation density, so it's a TeQ to the 4, so that's a TeQ, and then we have a TF by m chi and a TF squared. And then we will again assume that basically these ratios here are order unity. So freeze out happens when the dark matter particles become non-relativistic, because then you cannot sustain these kind of interactions anymore. Okay, so then if you plug all this in, so you have like one factor of n here, 3 here, so you can divide out 1, and you bring this to the other side, take the square root of this, and arrive at the following expression for the mass in this way. So we have the effective coupling, and now we have the Planck mass and the time of equality in this way. So remember that in the WIMP case, we had m chi about alpha. Then it was given by the geometric mean of the Planck's mass and the scale of equality, the temperature at equality. So you can say that this is a generalized geometric mean that is realized by SIMP production. If you plug in numbers, you find that what we have here is actually, hence the name, not the weak scale, but the strong scale that seems to be singled out. So if we use alpha f about 1 and m chi 100 MeV, that's exactly this scale that we get here. So it's the strong scale. And then, of course, for the same reason as for the WIMPs, people insisted on calling this a SIMP miracle. But by now you should start to become suspicious. There are a bit too many miracles around here. And you start to realize that, what we are doing is really, as I tried to stress before, it's dimensional analysis. So we have the Planck scale determined by the expansion rate of the universe. We have the time or the temperature at equality, which is just given by the fact that we want to reproduce the correct, the observed amount of dark matter. Dark matter should make up most of matter in the universe. And then we have one more scale. Yeah, so we're really basically exploring all possibilities of how to combine these scales in a dimensionally correct way. Yeah, and then of course you get different numbers. And that doesn't necessarily mean that it's a miracle that you get numbers that correspond to corresponding scales in particle physics. Yeah, so this is really what's happening. But I mean, who knows? Yeah, so it's an option. And okay, just to add on my comment here, you can of course generalize this to from like 3 to 2 to n to 2. And then you can do exactly the same kind of rational here, and you find that the dark matter mass is given by the effective coupling, and then n to the minus 1, m Planck to the nth power. Yeah, so, I mean, it's an even more generalized geometric mean. So there are many ways of deriving different scales, but, well, okay, it's countably many. Yeah? Okay. Good. And then let's get back to your comment. You have another one. Yeah, sure. Sure. At some point it becomes even non-perturbative. Yes, it breaks down. I mean, it can work. It can still work, but then not in a perturbative regime anymore. Yes, indeed. Okay, so now let's get to your comment. Yes, isn't it great? Yeah, so it's just a nice way of paraphrasing that we really don't know. Like with real miracles. Okay, getting back to your comment. Yeah, so this one here, this process, like in particular writing it in the annihilation way, so 3 to 2, what happens is that this actually heats up the dark sector. Yeah, so you basically have 3 massive particles to start with, and then you create 2, so you convert rest mass into kinetic energy. Heats up the dark matter particles. Yeah, and then, well, we need to do something with this. Yeah, because if dark matter is hot, this is excluded. Yeah, so we can't allow that. And we basically have 2 options. So one is an additional interaction with standard model particles. Of the type that we've discussed so far. Yeah, so let's parameterize this with a cross-section by some alpha psi. I mean, alpha coupling alpha psi. And this would basically cool dark matter continuously by these kind of scatterings to the standard model temperature. Yeah, that's an option. But that, of course, adds then observational possibilities, because this is an actual interaction with the standard model, so we can hope for some like direct search signatures. So option B is that we insist on this fact that we have a completely secluded dark sector. And this is referred to as cannibal dark matter. Yeah, so you see that people working in dark matter theory are sort of, well, they're inventive. So the place where this first appears is in the paper on self-interacting dark matter, where they describe this situation as follows, that dark matter cannibalizes itself to keep warm. Yeah, so that of course means that indeed the dark matter particles will be much warmer, have a much larger velocity dispersion than in standard freeze-out scenarios. So generically you will get very strong constraints from structure formation. Yeah, so you have to, make sure that the dark matter particles are sufficiently heavy in this case. But in general, so if it's really a secluded dark sector, it means that the entropy is conserved separately in the dark sector and visible sector. So we have conserved energy, entropy. So let's denote it with a small s. Yeah, so this is, well, in general, if you have, talking about entropy anyway only makes sense in equilibrium, but by assumption, this kind of diagram equilibrizes the dark sector. So then the entropy is given by this expression. But we want to look at the limit where the dark matter particles are already non-relativistic. So the main contribution comes really just from the energy density. So this is basically a t chi to the -1, and then an m chi, t chi, 3/2. And then, importantly, we have this exponential suppression, the Boltzmann suppression of the energy density. So what does that mean? Well, the entropy density is conserved. Yeah, so S chi A cubed is constant. Yeah, but A is the scale factor of the universe. So we are far into radiation domination. So the chi's will not affect the Hubble rate. So the A scales inversely proportional to the visible sector temperature. So, and if this is to be constant, it means that the temperature ratio actually has to grow exponentially. So you very efficiently, in other words, convert energy, rest mass energy, to kinetic energy. So you basically have to make up for this term here. So strongly increasing temperature ratio. So that means in order to have free streaming lengths that are compatible, you basically have to make sure that you start out with a temperature, an initial temperature in the dark sector that is much smaller than the standard model temperature. So concretely, so for example, for a dark matter mass of, what is the example here, 10 MeV, which is already much heavier than the Lyman alpha bounds on free streaming that you typically have for stereoneutrinos, for example, then you need an initial entropy that is smaller by a factor of 10 to the -5, or smaller by a factor of 10 to the 5 than the standard model or the total entropy density. So this is, like, entropy is conserved, so this I can apply to the relativistic phase. So when everything was relativistic, the entropies are just given by temperature cubed. So that means that I must start with a temperature ratio that is like 1 or 2 orders of magnitude smaller than 1. Otherwise, even an 10 MeV particle will be excluded by free streaming in these kind of situations. Okay. So let's attempt a kind of phase diagram also for this situation. So here I have the dark matter mass in GeV. I go up to 1 GeV, and my plot starts at around 10 to the minus 4. And here I put this, okay, now I just wiped it out. So this is the coupling to standard model particles, to heat bath particles. They are ordinary freeze-in-like couplings or elastic scattering couplings. And then we can sort of show what happens. So here we have a 10 to the minus 8, 10 to the minus 11. So if the, okay, we have basically 3 different regimes here. So here basically we have the annihilation rate from this term is larger than the 3-to-2 rate. So that means that the evolution will just be given by ordinary freeze-in or freeze-out-like interactions. So in other words, in this part of the parameter space, we have just ordinary WIMPs or freeze-out. Then as we decrease it, this is the kind of SIMP story that I have discussed, assuming that the temperatures stay the same. So we have efficient cooling from the scattering, but still a relic density that is set by 3-to-2 annihilations. And then if we sort of further decrease this, then we are in the cannibal regime. So then we have lambda cool smaller than 3-to-2. And if you wonder why these couplings here are so small for the WIMPs, this is because we are considering very small masses. So remember that freeze-out just fixes the ratio of the coupling to the mass, to the dark matter mass. And when we talk about weak scales, we mean weak scale couplings and masses. And if we have correspondingly lighter particles, we need correspondingly smaller couplings. Okay, so that's how far I wanted to get today. Any questions? I mean, there's plenty of time for discussions also the entire afternoon, so I guess we should go for lunch. Yeah, there was a question. Right, okay, so I forgot something. So please, for the exercises, remember to bring a laptop, if you have one here, because we want to look, at least in the second part of the exercises, at some numerical implementations. Okay, then let's go for lunch.